Hello everyone, welcome back to another video. Today we're going to be going over the problem solving and data analysis content area for the SAT and PSAT math section. This is going to cover a wide variety of topics, including like probability, statistics, as well as like ratios and whatnot. So make sure that you're understanding each of the content areas and especially each of the subtopics in the problem solving and data analysis area. So we're going to start off with ratios, rates and proportions. So what exactly are ratios? Ratios are just comparing two quantities to each other. It can either be like a part to a part or a part to a whole. So for example, if we have, let's say we have a recipe, right, that calls for 1 cup of sugar for every 3 cups of flour, right? We can write this ratio as like 1:3. This colon means is to, or it can be like 1/3. Both work as well, but this is a ratio. We're comparing a part to a part. Or we could do like 1 cup sugar to 4 cups of sugar and flour, or we can write it as 1/4. So these are examples of ratios. Proportions are kind of like an extension of ratios, where we have, let's say, again, with the 1 cup sugar over 3 cups flour. And let's say we want to find how many cups of sugar we need for 9 cups of flour, for example. So basically a proportion is where you're comparing two ratios, like it's an equality between two ratios, basically. So you do something called cross multiplication, where we take this top left value and multiply it by the bottom right one, so like this, and then multiply the bottom left with the top right, like this. So that way we get 3x equals 9, because 9 times 1 is 9. So when we divide by 3, we get x equals 3. So we need 3 cups of sugar for 9 cups of flour, which makes sense, because 3/9, that ratio, if you were to divide the top and bottom, the numerator and denominator, by 3, which would be the greatest common factor between both numbers, you get the same ratio of 1:3. So proportion, you're setting two ratios equal to each other. And then rates are basically ratios, but you're comparing different units. So for example, if we do 50 miles per hour, right? Technically we can write that as 50 miles divided by 1 hour. So this is an example of a rate. We have a ratio here, the 50/1, which can be simplified to just 50. And we have different units for the numerator and the denominator. We have miles in the numerator and hour in the denominator. So that's what a rate is. You're dividing two numbers with different units. So now let's move on to unit conversion. So unit conversion is important in terms of if the SAT asks you to convert, let's say, 12, I'm trying to think of a good one. Let's do 12 miles per second. No, I don't like that. Let's do miles per hour, actually. 12 miles per hour to feet by second. How are we going to be able to do this? How are we going to be able to make a conversion? So we're going to do something called unit conversion, or if you have done chemistry before, it's called dimensional analysis. Basically, we want to have rate conversion factors that we're going to be using to cancel out the units, so that way we get to our desired units of feet per second. So I'm going to write out this rate as 12 miles per hour, like this. All right, and then I'm going to draw a line here. What's going to come in this box, these next two boxes over here, is going to be our rate conversion factor. So let's say we want to convert to feet first, right? How many feet are in a mile? It's 5280 feet, right? So we'd have, you want your units to cancel out like crosswise, like we've been doing for like cross multiplication for proportions. So you're going to have 1 mile on the bottom and then 5280 feet on the top, right? And that makes sense because feet per second, that's the rate. So we want the feet in the numerator. So we're going to have feet in the numerator here. So now we're good with the feet part. Now we need to get the seconds part. So for hours to seconds, you can either do a conversion from hours to minutes and then minutes to seconds, or you can just go straight from hours to seconds. There's 60 minutes in 1 hour, and 60 seconds in 1 minute. So 60 times 60 is actually 3,600 seconds. We'll use that as our conversion factor. Again, we want 1 hour on the top, so that way we can cancel these out. These are 2 out. And then 3,600 seconds on the denominator. So now, when we cancel these out, right, we're going to get our conversion factor of feet per second, right? So it'd be 12 times 5280 over 3,600 feet per second. And if we were to use very quickly our calculator to figure that out, it would be 12 times 5280 divided by 3,600. So that gives us 17 feet per second. Remember, you can use a calculator on the SAT and PSAT. So that would be the answer there. All right. So that's how you would do a unit conversion. You want to make sure that you're using correct conversion factors to get from either your starting unit to your ending unit or to an intermediate unit. And you want to make sure that they cancel out in a cross way. So like with the miles here, how it crossed out the numerator and denominator, or denominator numerator for the hours. At the end of the day, your correct answer should have the units in their correct spot. So that's why we have feet in the numerator and seconds in the denominator, which is what we want. All right, moving on to the next topic of percentages. So percentages, it's basically a number out of 100 is a decimal form of it. So for a percentage, it's just that number with the percentage sign attached to it. So like 45%, right? What does this represent? It's really equal to 45 over 100. That's what this percentage sign truly means. So the decimal form of 45% would be like 0.45, which is the same thing as 45 over 100. So with percentages, where this is mainly going to come into play is if you have a question like, what is 20% of 300? And we need to find a value, for example. So 20% is the same thing as 0.2 because it's 20 over 100. 2 by over 10 is 1 over 5.2. And then of is like multiplying times 300. So when we do 0.2 times 300, that's basically going to be 1/5 of 300, or 300 divided by 5, which is going to be 60. So 60 would be the answer for this question. What if you could also get it the other way? You could get, for example, let's say we have 10 is 20% of what number? So in this case, it's like we have 0.2, because this is what 20% is as a decimal, right? 20 over 100.2. And then of, we can do it as if it's like x, right? 0.2 of a number, x, equals 10, right? 10 is 20% of x. So 0.2x equals 10. So to solve for x, it's just a one-step equation. You're dividing by 0.2. So x would be 100 over 2. You can move the decimal place over here and add an extra 0. So you'd get 50 as your answer. So 10 is 20% of 50, which does make sense. So that's the idea behind percentages. Make sure that if you're given like 20% of a number, like 20% of 300 like we did, then it's pretty simple. It's just that percentage is a decimal times the original number. If you're given it in this format, then you're going to be doing dividing. So you want to set it up as an equation. We have the percentage times x, that's the number you're trying to solve, equals your answer, right? That makes sense. It's just changing the quantity that we don't know. The number versus like the original number versus the number, like the 20% of that number, for example. So that's the idea behind percentages. All right, next topic, center, spread, shape of distribution. So this is where we get into kind of the statistics part of this content area. So measures of center is very important. Your measures of center are going to be median, mode, and mean, while your measures of spread are going to be range and other like and variation or variance, you could say, which can be also broken down into standard deviation. So it's center, spread, okay, and then shape. Okay, so With center, I'm going to go over center first. We specifically need to understand what are these three terms. What do they mean? So, no pun intended there, by the way. So let's try and come up with a data set, for example. Let's say we have grades on a test. Let's say we have 80, 84, 84, 86, 90, and 95, and 100, right? So let's say we want to find the mean of this data set. What is the mean exactly? It's the average of the data set, meaning you're going to add up the values here in your data set. So you're going to add all these values up, and you're going to divide by the total number of data points that you have. So it would be basically 80 plus 84 plus 84 plus 86 plus 90 plus 95 plus 100 divided by the total number of data points. We have 1, 2, 3, 4, 5, 6, 7. 7. So if we were to do that, I'm going to use my calculator again here. You can use your calculator. Remember that. 84. Oops, my bad. 80 plus 84 plus 84 plus 86 plus 90 plus 95 plus 100 divided by 7. And I get like 88.43 approximately. Okay. Typically on the SAT, you'll have answers that are a little bit more spaced apart, so you'll be able to accurately pick the one that is closest to this. Like you'll see like an 88, for example. That would be it. It's closest to that. All right. So that's the idea behind mean. How about mode? Mode is just the number in the data set that appears the most often. So of the 7 numbers here, which one appears the most often? The answer would be 84. 84 appears twice in the data set, while all the other numbers appear once. So your mode would be 84. That's pretty self-explanatory. And then finally, median, that's your middle number in the data set. So basically, how do we find the median? What I do is I would basically cross the lowest number and the highest number, and I'd keep going in that order until I get to the middle number, which in this case is 86. So that would be our mean. That's the middle number in the data set. Since we have an odd number of values in the data set, you're going to have an exact answer for your median. Like the median is going to be found in the data set. However, if you have an even number of numbers in the data set, like let's say we had 86 and let's say we had 88 up here, your median would actually be, you'd be down to these two numbers and you can't eliminate both. So in this case, you take the average of the two numbers in the middle. So 86 plus 88 divided by 2, which would be 87. And 87, that would be your median. So if you have an even number of numbers in the data set, you're taking the average of the middle two numbers, and that value would be your median for the data set. Okay? So now that's basically measures of center. Let's go over spread, and then we'll talk a little bit more about these measures together. So spread, what exactly is range? Range just refers to the highest number in the data set minus the lowest number in the data set. So what's the highest number here? It's 100. The lowest number is 80. And one thing I forgot to mention for median, you need to make sure that the numbers are in order for you to accurately do the median. So in this case, since the numbers are in order, we were able to find the median pretty easily, and it makes finding the range easy too, because you're just taking the last number minus the first number. So 100 minus 80, that would be 20. So 20, that would be your range, since it's just high minus low. All right? Now, standard deviation is something that you're not going to have to calculate it per se on the SAT or PSAT exam, because standard deviation, what it represents is it's like the square root of the sum of the squares of each value, how much it deviates from the mean. That's basically the idea behind standard deviation. How much do the values deviate from the mean? So we found our mean to be like 88.43. So you do like each value minus that mean squared. You would add up all those values and then take the square root of that. You're not going to need to worry about calculating that on the exam, but you just need to understand what does standard deviation mean. And what it means is just like if you are within one standard deviation of the mean, you're going to have like a majority of the values for that data set present. within 1 standard deviation of the mean. And this kind of gets us to that idea of a normal distribution. So it's like a bell curve like this, right? Kind of this is a good bell curve. Actually, no, I can do a better bell curve than that. So let's do a better bell curve. But this is the idea of like a normal distribution. So it kind of like rises like this, and then it kind of goes down like that. So this at your highest point, that would be like your mean. And then like this would be 1 standard deviation above, 2 above, 3 above, 1 below, 2 below, 3 below, right? I'm just going to write it like this. But this represents like the number of, if it's positive, it's the number of standard deviations above the mean. If it's negative, it's the number of standard deviations below the mean. And the importance of this is just to memorize these facts. Within 1 standard deviation of the mean, both above and below it, you have 68% of the data in your data set for a normal distribution. For 2 standard deviations, you have 95% plus or minus 2 standard deviations. And then you have like 99.7% with plus or minus 3 standard deviations. So pretty much all of your data is present within 3 standard deviations, either above or below the mean, depending on if this is a normal distribution. So that's just something for you to remember. But standard deviation is just how far above or below values are compared to the mean. And just being able to interpret that is the most important part. All right, now we're going to talk about distributions a little bit. But before we do that, I want to talk about the concept of an outlier. So what exactly is an outlier? An outlier, actually I should not have erased all that stuff. Okay, I want to keep the data set. But let's talk about outliers. Outliers are basically values that are kind of, they don't fit in with the rest of the data set. They're either way bigger than the values in the data set, or they're way lower than the values in the data set. And being able to identify these outliers is very important because that can tell you which measure of center and which measure of spread is better to use to analyze the data set. So let's say, for example, we had a test score of 25, right? That's an outlier because it's way lower than everything else, which is around 80 to 100. So how is this going to affect our measures of center and spread? So it's going to affect the mean the most because mean, remember, is your weighted average. It's like adding all the numbers up and dividing by the total numbers. So you're adding 25 and you're dividing it by 8. So specifically, if we were to go back and do this on our mean calculation, if we were to add 25 and divide it by 8, our mean now dips to 80.5 from 88.42. So that is a big change, especially since your mean is no longer reflective of the majority of the values in this data set, right? With this 88.42, it fits in like right here, which makes more sense than this 80.5, which fits in here, which doesn't make sense because now 6 out of your 7 values in the data set, well, my bad, I should say 6 out of your 8 are above the mean, which is not correct, versus 3 out of the 7 initially, which does make sense. So on the contrary, your mode's not going to change at all, obviously, but your median isn't going to change either that much, right? Because if we were to do the median here, right, we do left to right like this, we're down to these two numbers in the middle, and 85 would be our median. And originally, it was, if we just did this, 86 was our median. So it only changed by 1 compared to our mean changing by 8. So whenever you see a data set where you have an outlier, you want to use the median as your measure of center because it's more resistant to outliers. Basically, it doesn't change as much and it's still reflective of the data set. Our median is still reflective of the majority of values in this data set of 85 compared to the mean, which is a lot lower now. In terms of spread, you don't want to use range because now our range, instead of it being 20, 100 minus 25, now it's 75. So that's not a good measure to use either. And you don't really want to use standard deviation either since that is affected by the mean. So since your mean is now 80.5, your standard deviation is not going to be reflective of what it was before the outlier. So you want to use something called interquartile range, or IQR. Basically, it's the third quartile minus the first quartile of a data set. You can imagine your median to be like your quartile 2. So you want to be able, your third quartile basically, to figure out the third and first quartiles. For third, we'll start with third quartile. You want to look at the values that are above the median that you canceled out. So that'd be these 3 values here. And cancel these out. So you'd be left like with 95, for example. 95 would be your quartile 3. And then here on the left, we have these 3 values. We're going to cancel it out, and we'd have 80 be our quartile 1. So 15 is what it is after the 25. If we ignore the 25, right, so we just have these 3 values for our first quartile and these 3 values for our second quartile, we're going to still have 95 for our quartile 3, but now it's going to be 84 for our quartile 1, because that would be these 3 values that are below the median. So 11 would be our IQR. So you see it doesn't change as much. So that's your measure of spread or variance that you want to use. The interquartile range and the median when you have data sets that are having outliers in them. All right, and then the last thing I want to touch on is just the shape of distributions. Specifically, there are 3 main types of distributions you're going to see on the SAT math section. You got this kind, you have this kind, and then you have like this. All right. So this is your normal distribution here. It's like a normal bell-shaped curve. Your mean and your median are going to be equal to each other here. All right. This is a skewed left distribution. All right, I'll actually write out the full name of it. This is a skewed left, and this is a skewed right. How can you tell which one is which? Look at the tail of the distribution. Where are the higher or lower values are? If your tail is on the left, it's skewed left. If your tail is on the right, it's skewed right. So in a skewed left distribution, your median is greater than your mean. And that makes sense because you have a lot of values that are at the, like you have values at the left end, the lower end of the spectrum that are decreasing the mean. So your median is going to be greater than your mean. And then here for skewed right, your median is going to be less than your mean, which makes sense because you have values on the higher end of the spectrum that are increasing the mean and pulling it up compared to the median. If you have a skewed left or a skewed right, you're using the median either way because that's going to be the most reflective measure of the majority of the data values in your data set. All right, so those are the 3 main types of distributions you're going to see. Remember, the tail of the distribution is how you can tell what type of distribution it is. All right, let us move on to the next topic. We're going to be talking about data representations now. So what are different ways to represent data? What are different types of graphs or figures? So specifically, we're going to go over bar graphs, dot plots, histograms, and line graphs. These are the 4 main types of graphs you're going to see on the SAT or PSAT, so I want to make sure you guys understand them. So what are bar graphs? Basically, they're kind of like displaying the amount of certain like categories. So if we have like a bar graph like this, I kind of want to make this a different bar. Like if it's like here, we have one that's small. Like let's say these are like color socks, and we have like frequency here on the left, on the y-axis, and like color here of socks, right? Let's say we have red, blue, green, and yellow. Okay, so on a real bar graph, you're gonna have equal spacing between the bars. I can't draw that for some reason, but pretend there's equal spacing between the bars. But what it does is it helps you see the frequency for different categories. So if you have categorical data, meaning it's categories like red, blue, green, and yellow, right? Those are not numbers. You would use a bar graph. And I'm going to tie this into a histogram a little bit. Histogram is when you have like a range of data for each bar instead of like a category. So in those cases, you could still have frequency as your y-axis, but your bars are going to be touching now, and they're going to be reflective of like more values. So like, for example, let's say we had, we're going to change it's not a category anymore. Let's say we have scores on a test, for example, right? Scores on test, all right? So let's say we have, we're going to have like this bar, and then this bar, and then this bar, this bar, and this bar. They would have the same like horizontal, horizontal length for the bars. I tried to make it as good as possible, but I feel like I still messed up a little bit. But pretend these have the same length. Let's say this is 1 through 20, 21 through 40, 41 through 60, 61 through 80, 81 through 100. So this is an example of a histogram. For each bar, you're having a range of values. So that means if you have, let's say, I don't know, 5 students who got scores from 1 to 20, that means that any of those students, the students could have gotten anywhere between a 1 and a 20. This is good if you want to look at like if you have like a large distribution and you just want to look and see like, where the majority of students scoring. You're not going to be able to really understand individual values from a histogram. It's more so like the actual distribution. Like, see, like this is like a bell curve because it goes up and it goes down. All right. So that's basically what a histogram is all about. Dot plots is a way to also count frequency of a value. And it's good if you're like actually wanting to see like the individual number at a particular point. So like, for example, we'll do the scores example again. So here's your scores, your frequency. And you have, like, let's say, you'd have to do individual values here. So let's say we do like 5, 10, 15, and 20, right? Let's say it's a 20 question test, right? Kind of bending my own rules here, but that's okay. You actually wouldn't really have this either. You would just have like a number line almost, and then you just have dots to represent the number of students who got that score. So if we had something like this, right? Basically, you're stacking dots on top here, and it's good to figure out individual scores for students. So like 4 students got a 5, 2 students got a 2, 6 students got a 6, 2 got a 20. It's also good to look at distributions. You see how it like kind of dips here, goes back up and dips. And it's good for just individual values compared to histograms, which is more so if you have like a range of values. All right. And then finally, line graphs. Line graphs is measuring the change in something over time. That's really good for that. So like if you have temperature, right? Let's say you want to measure the temperature in a particular city over a period of time. I don't know. I'm just going to do January, February, March, April, May, and June, right? And let's say we have temperature values, I don't know, 70, 75, 80. And you have like points like this. Kind of counterintuitive when you think about, seasons and temperatures in the Northern Hemisphere, but that's okay. I'm just trying to illustrate an example here. You have a line that would connect all these points. So like this, and you'd be able to figure out trends. So like what happens overall, we see it kind of like dips and then it goes back up and then it dips and then it goes back up. So there's not really a big trend here. But if you do see a trend, like it's mostly decreasing or it's mostly increasing, that's what really line graphs are good for. They're good for trends overall. All right. So those are the major types of ways that data is going to be represented on the SAT or PSAT. It's really important to be able to understand what each graph means and being able to identify specific points on one of the graphs or identify trends if you're given a line graph. So make sure that you're able to understand how to read these graphs. Typically, if I was given a graph without any knowledge of what's going on, I'm looking at the axes first. Then I'm looking at, if there's a legend, kind of what do these points mean? And then is there trends if it's like a line graph or something? And then I'll be able to, if it's asking for like a specific point on one of the graphs, I'll be able to look and locate that point once I understand the graph as a whole. All right. Let's move on to the next section of scatterplots. So scatterplots are also another type of data representation. I didn't mention it before because we're going to talk a little bit more about it here. But scatterplots, basically you have 2 variables. They may or may not be related. We don't know. Let's say we have, let's do temperature. No, I'll do temperature here. Temperature and ice cream sales. right? And scatterplots are going to be like a bunch of points like this, for example. It's kind of random points. I'm putting it everywhere. But what does a scatterplot tell us? It tells us correlation, and so like what type of relationship it is, what's the correlation between it, and what's the form, like how strong is the correlation. So specifically, we see that we have a positive correlation here, right? As the temperature is increasing, so are the ice cream sales, right? We can see that it's a mainly linear relationship, right? We see that the dots are mainly going up. There's a couple that are kind of scattered around there, but it's mainly going up. And if you actually know the correlation coefficient that's symbolized by R, it can be in between 0 and 1. 0 means it's a weak correlation, 1 means it's a strong correlation. You can determine whether this is a strong linear relationship. Typically, if your correlation coefficient is above like 0.8, then it's strong. If it's like 0.5 to 0.8, then it'd probably be moderate. And then if it's under that, it's probably weak. But that's what a scatterplot can tell us. We can also use a scatterplot to find the line of best fit. So if we're given a line of best fit, like it should be going through the majority of the points. You should have an equal amount that's about above or below, approximately. Again, it's line of best fit. It's not going to go through every single point. You would be able to find the equation for the best fit line and then try to predict where points would be for like a higher temperature or something. So just out of randomness, let's say we got our best fit line as y equals 10x plus 12. Right? Let's just say that. Actually, no, we'll keep it. We'll keep it like this. Okay. It's a little bit of a crazy example, but let's say that we want to figure out how many ice creams are sold when the temperature is 70 degrees, right? So in this case, we are like extrapolating the data. We're predicting what a data value would be, giving the line of best fit. So we just plug in 70 for x because that's our temperature, and then we would simplify it. 10 times 70 is 700 plus 12 would be 712 for your ice cream sales, which honestly, never know, right? But this is just an example. Another question that could be asked from a scatter plot is like, let's say you're given a actual data point. Like let's say this one here, this one seems to be above its, where it says it's supposed to be on the best fit line. And let's say we need to find this distance between the best fit line and the actual point. In statistics, this is called a residual. But basically, let's say at this point, right, it's 4,105 on the best fit line, but in reality, this point up here, the actual like data point is 4,125. So what's the difference between them? You're just subtracting the points here. It would just be your actual y minus your predicted y. So it would be 20, for example. And if you end up getting like a negative value, then you can just do the absolute value of it to figure out the difference. Typically, if it's negative, that means, well, if it's positive, that means it's an undershoot on the best fit line. If it's negative, that means it's an overshoot on the best fit line. So that's just a little bit more statistics for you guys to know. Okay, so that's the idea behind scatter plots. Be sure to know like trends, relationships, and best fit lines. Those are the biggest things from scatter plots. All right, linear and exponential growth now. So linear growth is basically you're changing by the same amount, right? So if we had a table that was like this, and it was like 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, right? We're increasing by 2 every time we increase x by 1. That's called linear growth. Exponential is different though. It's going to be increasing at a faster rate for exponential growth. So it'd be like 1, 2, 2, 4, 3, 8, 4, 16. So it's like multiplying by 2. So you're multiplying by a common factor for exponential growth, while for linear growth, you're like adding or subtracting like a certain amount. So how do we write these as equations? Obviously, we've talked about linear equations, right? Our y-intercept, that's 0. Our slope, it's increasing by 2 as we increase by 1, so it's 2x. So y equals 2x. However, for an exponential function, it's a little bit different. It's in the format y equals b times r to the power of x. So what does this mean? B is like your initial value. So like, what would be like your y-intercept, for example? So in this case, our y-intercept would be 0, which actually wouldn't make sense. Actually, I don't know why I put that, because you wouldn't do 0. 0 times 2 wouldn't be 2. My bad. So it'd be 0, 1, actually. Because as you're multiplying this times 2, you're multiplying this times 2 as it increases by 1. So our y-intercept is going to be 1. We don't really need to include it, because if it's not there, it's considered to just be 1 times that. R, that's our ratio. So as we increase by 1, what are we multiplying by? In this case, it's 2. So 2, and then it'd be to the power x. That would be how you would write a exponential growth equation. So if x is 2, right, what would y be? 2 squared, 4. That's what we see here. If x is 4, what would y be? 2 to the 4th power would be 16. That's what we see here. So that's how you'd write an exponential equation. Typically in the SAT, you'll get problems like where you have like someone that's like investing 10% of their savings into an account, and it's like being, it's 10% every single month. So it's like your equation would be like whatever you put in initially, let's say $10,000, and then let's say it'd actually be interest. So like let's say you'd have an interest of 0.1 or 10%. You want to convert it to a decimal, by the way. 10% every single month, where x is your number of months, right? And let's say you want to figure out how much interest has accrued on your account in 3 months, for example. So you just plug in 3 for x and solve for that. Remember that over time, exponential growth is always going to be greater than linear growth, assuming that it's exponential growth. So in other words, this rate here, this r, needs to be greater than 1. If it's less than 1, then it's exponential decay. It's going to be decreasing. So if we were to look at this on a graph, exponential growth looks like this. So it's like kind of level, and then it kind of goes whoop. And then for a exponential decay would look like this. It starts out really high, and then it starts to like a very rapid decrease before it hits kind of that. It's basically a horizontal asymptote. It's a point that it's not going to cross, but it's decreases really fast, and then it's like just pretty much stagnant for the most part, or it decreases very, very slowly. So that's the idea behind exponential growth and decay, as well as linear equations. All right. So remember, if you're ever comparing linear to exponential, if it's exponential growth, it's always going to be bigger than linear at some point. Linear might be outpacing it at first because maybe you have like a higher y-intercept or something, but over time, eventually, exponential growth is going to overtake linear. All right. Now let's move on to probability and relative frequency. So what exactly is probability? Probability just refers to a desired outcome over all the outcomes, right? That's your numerator over your denominator. So, for example, a pretty simple example, let's say we have a drawer with 2 red socks, 2 blue socks, and 4 green socks. And we want to figure out the probability. If we were to randomly pick one of the socks in the drawer, what is the probability it's going to be a green sock, for example? So green sock, that's what our desired outcome is. So there's 4 of them, so we could pick any one of the 4 over your total number of outcomes, right? So out of all the socks in the drawer, we have 2 red, 2 blue, and 4 green. We can add those up and we get 8 socks in total. So the probability of pulling out a green sock would be 1 over 2. That's an example. Remember, your probability, it needs to be between 0 to 1. It can be inclusive of that, where 0 means there's no chance it's happening. 1 means there's an almost certain, well, I'm sorry, not almost. It's going to happen. It's a certain chance. If you're close to 1, then it's an almost certain. It's important to know when we should like multiply and add probabilities together. So if they're independent events and you're doing like 2 of the same thing, like let's say flipping a coin twice, right? The outcome that you get on the first flip is not at all affecting how the second flip is going to go. that's where you'd multiply probability. So if you want to figure out the probability of doing 2 heads in a row, flipping 2 heads in a row, right? It's 1/2 for the first flip to get a heads, and it's 1/2 for the second flip. So to get both in a row, you'd multiply them together and get 1/4. If you have a situation where it's like with the socks example, like what's the probability of getting a red or a green sock? That's where you're adding probabilities. So if we go back to that problem, right? Let's say we are trying to find the probability of having a green or a red sock. If we were to pull out a random sock, what's the probability it's a green or a red? So in this case, it's almost like you're adding this 4/8 plus 2/8, adding the probability of getting a red sock. So when we do that, we get 6/8, which can be simplified to 3/4. So you have a 3/4 chance of getting a green or a red sock. So make sure you're paying attention to wording. If it's saying and, it's more likely to be multiplication for your probabilities. If it's or, it would be adding. And then let's talk about relative frequency. You're going to see the idea of relative frequency in like two-way tables. So like, for example, let's say we have, trying to think of a good example. Let's say we have like teachers, for example, like John, Joe, and then total. And then let's say, for an exam, for example, let's say students who pass and then versus fail and total. So this is an example of a 2x2 table, or like a it's a for relative frequency. It's a two-way table. So let's say we have values of like I don't know, 50. I'm gonna do this in a way I'm gonna teach you guys how you can fill in the rest of the values of a table, only being given certain values. So let's say 50. 25, 100, 65, and yeah, I think that's all we need. We only need, yeah, that's all we need. Okay, so we're gonna use these values here, and we're gonna try to figure out all the other values in the table. All right. So the easiest way to do this is to look for a column or a row that has 2 out of the 3 items filled out. That would be the John column here, right? We have 50 and we have 65. If the total is 65, that means the total students who failed, right? Pass plus fail gives you that total. So 65 minus 50, we get 15. So that would be that column, all right? Same process now. Which column or row has 2 out of the 3 boxes filled? All right, the fail row does. 15 and 25, right? We have to add John plus Joe to get the total for the failed. So 15 plus 25, that gets us 40. Same process again. Which column or row has 2 items out of the 3 filled? Oh, the total column. That has 2 out of the 3 filled, right? Our pass total plus our fail total will get us our total in total. Okay, that was kind of weird, but you guys get the idea. So to get the pass total, we just do the total minus the fail total to get 60. All right. Now, John, we could either do John, for the pass total, like this row, the pass row, or the total row, doesn't really matter. We'll do the pass row just to start. So if we have pass, John's passes is 50, the total pass is 60, so Joe's is going to be 60 minus 50, which would be 10. And then finally, down the line here for the Joe row, 10 plus 25 gives us 35. So we just needed 4 values, and we were able to find the other 5. All right. So if you do get that on the SAT or PSAT section, it'll more than likely be like you'll have to kind of do solving for the numbers. It's not going to be like every single number you fill is going to be like an answer per se, but it's like you're going to have to get to a certain number, and you're going to have to fill in certain numbers in the table to get to a particular number. All right, so now let's get to the idea of frequency. So remember, with frequency, it's similarly to probability, where we're trying to find desired outcome over the total outcomes, like in the particular question. So like, for example, if we have the question, what is the probability that one of Joe's students passes? So we're going to look at the Joe column. So our probability, right? So what is the probability that one of Joe's students passes, right? So Joe's students, right? So our total is going to be the total number of Joe's students, which would actually be 35, right? That makes sense because we're only looking at Joe. We don't care about John right now. So for Joe, it'd be 35. And then the probability that the student passes is just Joe's students who passes, which would be 10 over 35. If you were to simplify this by dividing the top and bottom by 5, you'd get 2 over 7. All right? Another example. What is the probability that out of if one of the what is the probability out of the total number of students if we were to select a student from John's class who passes? So in this case, it's saying out of the total number of students. So that means we're not using 65 because we're doing total number. Our denominator would be 100. And we're looking for the probability that it's a John pass. So one of John's students who passes. So that would be 50. That would be this cell right here. So 50 over 100, that gives us 1 over 2 as the probability that we're getting a John student who passes from the entire body of students. So this is really important, guys. You need to understand the probability question that's given to you, because in the question that will tell you your denominator and your numerator, like what cells in the table you should be looking for to determine that. So if it's saying like out of a certain amount, right? That's like your denominator. And if we're saying like how many of so-and-so did this, that would be your numerator. And remember that it should always be, your probability should always be between 0 to 1. And being able to identify the numerator and denominator is important so you know which cells to look for to answer the question correctly. Oops, do not want to move myself. I want to erase. All right, so let us go ahead and move on to the next topic now of data inferences. So basically what this topic is all about is about like samples and populations and proportions from those. So population, when we're talking about like studies, for example, a population is like the largest possible audience you want to generalize your study to. So when you're picking a sample, those are actually like the group of people that you're going to be doing your study on, right? Because most of the time, doing a study on a population, it's just not practical, right? Because you have to account for every single person and it's just not feasible. So you want to use a sample that is representative and random, meaning that it's able to reflect everybody in the particular population, and it needs to be random to ensure that it can be truly generalized to the full population. So when you're looking at data inferences, right, you need to first make sure that the sample is representative and it's random. And you're going to be looking at proportion. So you're going to be given like a sample proportion, and you're going to have to generalize it to the population. So for example, let's say we have city A that has 1,200 people. And let's say a study was done on, it was a representative simple random sample that was done on a sample of 400, no, actually I want to make a smaller value than that. It's done on 200 individuals, and they found that it was like for a, whether they support or are against a tax bill, for example, right? So let's say out of those 200 people that we put as our sample, out of our 200 individuals, 50 of them, actually I shouldn't write it like that, to be honest. Out of our 200, 50 of them said yes to the tax bill. So from that data, how many residents in city A would support the tax bill? So you're using your sample proportion, and then you're almost going to like get an equal proportion in the entire city. So I would do 50 over 200. This is your sample proportion. The amount of people in the sample that said yes over the total number of the sample equals 1,200, the total number of people in city A, over the total number of people in city A that would be in support of the bill. So in this case, this is just a simple cross multiplication one. To make it easier on you guys, I would actually try to simplify the fraction out first before we cross multiply. So 50 over 200, right? 200 goes into 50 4 times. So I'd make this actually 1 over 4. And then I'd cross multiply. I'd have 4x equals 1,200. So x is 300. So 300 individuals would be in support of the bill. If you had it in a percentage, like if it was like 38% of the sample, they'd still give you, like, let's say 30% of like the 500 people in the sample, you would find that proportion of people, like you'd find 30% of 500, and then you'd like do the same thing, set it up as a proportion like this, and you'd be able to get your answer. All right. And on the last topic, I kind of already talked about it a little bit while I was going over it here, but statistical claims, you just need to make sure that for statistical claims, you are making sure that the sample where data is coming from is both representative and random, meaning that it should accurately reflect the population as a whole. The result should be generalizable to the population. If there's any flaw in survey methodology, like if there's a certain amount of bias, if it's not accurately reflecting the population, like let's say it's like convenience sampling, you're only picking people closer to you, or undercoverage bias, you're not accounting for all members of the population, then you cannot generalize the study's results to the entire population. So you'll get questions in the SAT or PSAT that's like, given what the researcher is doing, can they accurately take their claims and the results from their sample and generalize it to the population? So you need to make sure it's representative of everyone there and it's a random sample, so that way you can accurately generalize. If either one of these conditions are not met and you find a source of bias, then you cannot generalize the results to the entire population. All right, everyone, so that is the problem solving and data analysis content area. Again, this is a very important content area, just like the other ones on the SAT and PSAT. So make sure you understand all the different concepts in this content area. Thank you guys so much for watching again. Please make sure to like and subscribe. And please let me know if there's anything I can do to help you guys out with any sort of questions that you have. And I will see you all in the next video.